Okay, so we'll go ahead and get started. The main announcement is this is the last lecture before your first module exam, and that will open today at 2:15, and you'll access it through your ZipGrade account. So the purposes of those bonuses that you did was to make sure that you can log in, you can see how to navigate the ZipGrade. The exam will be open for 24 hours. The time limit is 24 hours. So whenever you start, there's no like sub-limit within that. There's 30 questions. Please make sure that you read those, you're answering in the electronic bubble the question that you think you're responding to. And then when you're done, please review and make sure you submit it. So it will close at 2:15 tomorrow, and after that I will upload the answer key and it will auto grade. Then I'll release this exams to let you see them online. So you can log into your account, you'll see what you got right, what you got wrong, and then you'll see your point total. So your scores are available in ZipGrade. They won't be in Canvas until I move them over there, and that will be later on at some point. So I would encourage you to download the Excel file that's on the syllabus main page of the Canvas so that you can start tracking your points up until this time in the semester, and then it'll project out your letter grade. Any questions on the course mechanics or exams or points or grades before we get started? Yeah.
Can you show us how the Excel sheet works properly?
How the what?
Excel sheet works to calculate a grade properly?
So you definitely need to download it onto your computer. So if you just click on Canvas, it's going to show you an image. So you need to download it, open it in Excel, and then within there, there's cells that are highlighted in yellow. Those cells should have no numbers in them. Don't put 0 for any other exams, just leave it empty, delete any numbers. So the points that you got for whatever the assessment, that's when you put it in. And basically, I figured out a way to do this after 30 years of working with Excel, how to do it in real time rather than for all of the points for the semester. So say there's the 60 exam points for Module 1, whatever you get plus your bonus, it'll project out a letter grade for just those points. And as you earn more points, you put it in there, and you have to have all those yellow cells filled before it can understand the course grade. So in real time, it's not of all of the course points, but you're just putting the numbers that you earned in. So today we're going to wrap up on a chemical understanding of color, and then we'll talk about a little bit how these conjugated molecules are made in nature, and then what are some of their uses, and hopefully I can get through all this so that it's not like you don't feel rushed. So maybe around 2, hopefully I get there by then. We'll do a little attendance bonus, and this time the perceptions on smell. So you'll see what some of these molecules are their applications. So we left off on talking about these extended conjugated systems. So now we'll look at the structural properties that are required to see something in the visible region. That's the perception of our sight. And the guidance for this was, through history, the scientific endeavor has been recognized by Nobel Prizes that are important for advancing science. And so, we see these words: carbohydrate, vitamin C, carotenoids, vitamins. What are these structures and classes? So we're talking about color. And so what is a carotenoid? So it's kind of, you can make the association in there. Just think of like carrot, and you think of orange. Carotenoids are polyunsaturated. So again, that means many. So we're talking about molecules that have many alkenes. Specifically, the alkenes are separated from each other by a sigma bond, so they're conjugated. It says they're hydrocarbons, so just C and H. And then I have this word in here, tetraterpenoid, and we'll talk about what that nomenclature is. Terpenes are a class of molecules. And then the family or the bigger class are called lipids, which you've probably heard of. So carotenoids are typically yellow, orange, or red. And then from there, the pure hydrocarbon ones are called keratines. And then ones that have oxygen are called xanthophylls. And we talked about, the color we perceive, that the molecule is transmitting light, but it's absorbing the complementary color. So because they appear yellow, orange, and red, and that's this region of the electromagnetic spectrum, they absorb violet to green light, and so that's the other region. So when we think of light, we think of the rainbow, Roy G. Biv. But then what does that mean? So depending on which way you're walking on that spectrum, red light, again, has a longer wavelength than violet light. And then the energy relationship is inverse. So make sure that you can be kind of fluid in that understanding. So the molecule shown on this slide here is called lycopene. It's a photosynthetic pigment. Any polymer majors in the crowd? Handful. So this will be of interest to you because we all have screens, right? So like these screens, like there's LCD, that stands for liquid crystal display, but nowadays they're OLED. What does that stand for? OLED. Anybody? Bueller? Organic light emitting diode. So the organic is an organic molecule that is polyunsaturated, and it's been specifically tuned, to do some sort of response. So like an electrical stimulus, then it's going to shoot out some photons, light that you can see. So lycopene is a naturally occurring pigment that gives the red color to fruits. So watermelon, grapefruit, papaya. And just take a look at that structure. I have the molecular formula here. You see that, C40H56. We'll find that, these classes of molecules sort of go in groups of 5. And when you look at lycopene, do you see a pattern repeating in there? So yeah, except for the middle, there's a break in the pattern. So the pattern is telling us something about how nature is constructing that. So the pattern is 5 carbons. So 5 times 8, that gives us the 40 total carbons. And I'll highlight in red here. I'll do it over to the right here. So there's 3, 4, and 5. So that pattern repeats. And for the polymer majors, you can think of that pattern as a monomer. So mono means one, that's the building block. Polymer means many of the monomers. And so they're bonded in this fashion, but then as we observed here, there's this break in the pattern. And so that where I drew that line, there's almost like not a true mirror image, but say if I put a dot, instead of using a mirror image where that dot is, imagine that's an axis, like a pole or a rod, and you rotate it 180 degrees, it would then match up with itself on the other side. So lycopene is transformed into beta carotene. And if you watch any sort of TV, you probably watch Netflix or something, but on TV there's these things called commercials, and they're trying to sell you stuff. So usually they're, hey, take this natural supplement, it's got beta carotene in it. So you've probably heard about it. So lycopene is transformed into beta carotene through this thing here. So this enzyme, lycopene cyclase. And if you go on to biochemistry, you learn a lot about metabolism. And then when we normally think of metabolisms, like you eat and the food gets metabolized, but there's these metabolic cycles chemically, and those occur with enzymes, and enzymes always end in ASE. And you can see the front part of it kind of looks like cyclic. So it's going to take part of this molecule and cyclize it. And we can see that reflected in the structure here of the beta carotene. Now at the ends, we have these two 6-membered rings. Notice the molecular formula is still the same. So overall, the reaction of lycopene to beta carotene, it's an isomerization. The molecular formula is still conserved. We've just changed some functional groups. And carotenes transmit energy they absorb to chlorophyll. So any plant people in the crowd, biology majors, conservation, that sort of thing. So, sunlight is giving energy, and then the plants, how do plants get carbon? Why should we have a lot of trees around? What do plants breathe in? CO2. So plants get carbon from CO2. So we do the opposite. We breathe in oxygen, and then we exhale CO2. So the reaction of oxygen to carbon dioxide, that's metabolism. So where do we get our carbon from? The what? So we get carbon from glucose. So you can think of like sugar, carbohydrates. Glucose is the primary source of our carbon. So we breathe in air, we have glucose, it gets metabolized, the glucose gets chopped up into CO2, and that's what we exhale. And interesting thing, we'll talk a little bit in Module 5 about if you have a scale at home in your bathroom. Yeah. So weigh yourself at night and then weigh yourself in the morning. You ever try that? So what happens? You lose weight, but you're sleeping, you're not exercising, so what's happening? It's just the respiration.
Oh.
So a normal kind of adult can lose about a pound or 2 every night. Athletes, like 3 to 5 pounds, just based on the metabolic activity. But that's how you're losing weight, is through CO2, which is a gas. So you're exhaling a lot of that as you sleep. So there's more like red and orange and yellow, green kind of fruits and vegetables, and the darker colors are a little bit more rare. So like blueberries, black raspberries, eggplant, grapes, red cabbage, they get their color from a different type of molecule. And, naturally speaking, I'm not sure the pathway by which these are made, but it's probably not the same as the other ones, because we can see there's rings and they're aromatic rings. So it's probably some other pathway. But these are called anthocyanins. And what's weird or interesting about them, see that oxygen? It has 1, 2, 3 bonds. And then it will have one lone pair that gets it the plus charge. And that functional group is called a flavillum cation. And see all these R groups? Those are just substituents, and typically they're like glucose. So because these are found, in fruits and vegetables and plants and stuff, basically there's a reactive group there that just hooks a glucose on there.
So
Yep.
it's only the outer layer that it affects, because I know when you cut open certain vegetables or things like eggplants, they're kind of like green on the inside.
Yeah, so that probably has something to do with like the amount of sunlight that's hitting it and how it's just produced on like the skin or the shell or whatever. Anyone like flowers and botany and stuff? So it's fall. I haven't been up to the front of campus. I don't know how the flower garden's doing, but like usually in spring, there's some pretty vibrant looking flowers there. And there's the typical red roses and all that stuff. But when you get into the more unique colors, like this class of compounds has a property called halochromism, which means they can change their color based on the pH. So there's some flower that does that, right? Like it changes color from like something to something else based on the acidity of the soil. Might be like lilies or something. So that's an indicator of like the soil quality as well. So the next couple slides here I ripped out of a chemical and engineering news publication from the American Chemical Society that sort of demonstrate this process of the perception of light. This Roy G. Biv here, let's just think of that as kind of sunlight. So it has all of these different wavelengths, and we're just perceiving it as white light. And then this colored dye, which we see as blue, is acting as like a filter. So because it's blue, that means it's absorbing the complementary color, which is orange. So that's a way of thinking about color now, is whatever you perceive, the complementary color is being absorbed. So the Roy part here is being absorbed. What you perceive is being transmitted. So like these, when I was a kid, we used these to like dye eggs for Easter. You dip a little bit in and then the other side, and you can make these patterns and stuff. So the dye is like a filter in a sense. And then we can see for the red, we see red here, so it's absorbing over here. And again, for reasons why that's interesting, you know, the dye is a molecule. And if you start playing around with the functional groups in there, then you can tune where it's absorbing and then what gets transmitted. And that strategy or thought process is what goes into like the design of these OLEDs. So artificial dyes are a hot topic now. You know, this Make America Healthy Again, where we want to remove anything that's non-nutritive in food substances. You know, so, you know, I enjoy Fruity Pebbles, Fruit Loops. I like these highly colored cereals. And I like the taste, but I mean, the appeal is the color of it. But the color it doesn't do anything for you to give you energy. It's just there to create an emotional bond. And, you know, since they don't do anything, there's speculation, hey, these things cause cancer or something like that, but that stuff's not proven, really. And so there's this drive to just get them out completely. Like, you know, if we're making this cereal for something, why are we adding this other stuff in if there's no benefit to it? But in terms of artificial dyes, you know, they have these just like generic names. Yellow dye number 5, if you like M&Ms, that's what makes M&Ms yellow in that color. The name of it is tartrazine. And then they have these really, you know, if you look at all the heteroatoms in there, nitrogens, oxygens, sulfurs, and then there's some ionic stuff. So they're typically, you know, have these functional groups with heteroatoms that kind of pep up the color that they transmit. But I mean, this is just a smattering of the most well-known. There's hundreds or thousands of dyes. And, you know, think about the importance of color for all of us. I tend to be pretty muted here in my my fashion. But the importance of color to humans in history, you know, the color mauve, which would kind of be like a little bit more purple than that. Mm-hmm. So mauve is called royal purple. And why is that? So when these dyes were extracted from plants, humans noticed, hey, that stained my, what fabric did people use back then? I think it has another name. I don't know if it was cotton-based exactly. Just imagine it's like, you know, 3,000 years ago, you got some like dirty robe thing on. It probably wasn't a cotton blend, but maybe silk. So if you were well-to-do and had money, you had better clothes, and then you could get those clothes differentiated from the poor folk. And if you had colored clothes, that meant you had some nobility, you had some sway in society, and that was really a driving force for the chemical dye industry to start, where a lot of organic kind of nucleated from. So once you have a product, you sell it to rich people, you start a business, and you try to take over the world. So I apologize, these slides are a bit dated, but there is a structure of red dye number 3. And I mean, you can see all the conjugation in here. And notice these like sodium plus O minus. The oxygen has 3 lone pairs, so it's negatively charged. And what does that mean? it can put those electrons into these rings. And if there's more electron density in there, that's going to pep up the saturation or hue. I don't know the difference of those words, but it increases, the perception of that color. And then I guess what's interesting here is this conjugate base of the acid can then do some reactions over here. And then people will study these things to make these like switches. So say in this form it's on, but some reaction happens and then it turns off. And you can adjust that with the pH of the medium. So we've all heard of chlorophyll. Typically you think of like that's the thing that makes plants green, and then this is the structure of it. So I'm not terribly versed in biology. It didn't interest me too much, so I'm sure all of you know more of this than I do, but this molecule is used in the electron transport chain. So again, it's the transfer of this energy for metabolism to happen, to produce things or degrade things through metabolic processes. We're going to learn about a couple different scientists named Fisher. This Fisher was awarded a Nobel Prize for the research into chlorophyll. And then this other molecule, Heyman. So plants use this. See the metal there, magnesium? This part of the molecule is flat, and then there's this cavity in there that magnesium sits. So what is the name of the structure that humans have, and what's the metal inside? So yeah, hemoglobin, and then iron sits in the middle. So when you breathe in the O2, it goes into that iron, and then stuff happens, and then it comes back out as CO2. So how do we, as scientists, quantify the color? How do we know what the exact wavelength of something is? So we use UV vis spectroscopy. So UV, again, is ultraviolet, visible. They're kind of lumped together. And then remember that the word spectroscopy is how light interacts with matter. And so as we move back and forth on the electromagnetic spectrum, because there's different energies associated with the wavelengths of light, when they interact with matter, they're doing different things. So radio waves were used for NMR. Infrared was used for disturbing the dipole moment of a bond, for bond stretching. And then we'll see the phenomenon for UV vis in a couple slides here. How much energy does it have to make something happen in a molecule? What exactly is it doing? So in the UV vis region, the energy promotes an electron from the highest occupied molecular orbital, so a filled orbital, into an anti-bonding orbital, so lowest unoccupied. So you have orbitals with electrons, then you have these other ones which were called anti-bonding in higher energy. They're unfilled. They have to exist, because when we make a pi bond with two p orbitals make the bonding orbital, but that's just one, so we need this anti-bonding orbital. So here's the equation from physics. there's these relationships between the Planck's constant, velocity of light, and then c is the frequency of the light, c is the speed of light, and then lambda is the wavelength. So you can do some algebra and move things around. And what ultimately falls out is this equation here. Remember the name of that equation? So Beer's law, Beer-Lambert law. So the absorption is equal to the log of the intensity of the reference beam divided by the intensity of the sample beam. So a way to think about that is when there's nothing in there, there's 100% absorbance. And then you put a sample in there, no matter what, it's going to absorb some stuff. And then it's adjusted to the log scale to make the numbers understandable. So the main term in here that's kind of important is this epsilon, which is the molar absorptivity. That's kind of the quantity at which a substance can absorb light. How much can it take in, and what's the response or output of the signal? So let's run through these relationships again. I'll start putting some compounds on the slides, and then we'll talk about why things are colored. So here is the visible region. And again, even though we say Roy G. Biv, the Roy part is on the right side. And then it kind of moves this way. So we have the violet, and then the ultraviolet would be over here, the red, and then the infrared over here. So here's the different color regions, and then their associated wavelengths and nanometers. So, if we think from 400 to 800, what that's saying is, from the highest part of the wave to where it completes one cycle, that would be, say, 800 nanometers. It's just a distance for the red. So because that wavelength is long, it's lower energy. As you start compressing the distance so it's shorter, that's what makes it higher energy. So, yeah.
Sorry. Back to what you were saying earlier. I remember learning how in older times purple was the color of royalty, was harder to make. Is there any chemistry background to why purple is more difficult?
So I think the story kind of originates in England and Germany, and one of the main scientists was Perkin, and they wanted to find out what's responsible for the purple color, that mauve. And so they were isolating things and getting molecular formulas and trying to propose structures. And all this was happening before people knew about hybridization and how carbon bonds and stuff like that. So at that point in time, it was just easy to collect a bunch of plants and extract it out. Making it through reactions, the knowledge and understanding just wasn't there yet.
Okay.
So let's look at this series of compounds here. So we have a single alkene, that's ethene, and then all we're doing is successively adding in another double bond, again separated by the sigma bond. And what we want to look at is, how does this term here, lambda max, change? And again, that's the wavelength at which the compound will absorb light. So when we look at this scale, the ultraviolet is 380. So as we're moving to the left, that number is getting smaller. So the 171 is somewhere over here, meaning that we can't see that or see it with a color. This last term, or the last row, I'll talk about in the subsequent slide. What does that mean? So we're gonna put in a double bond and see how the number changes. It's now migrating back towards the right. If we take the butadiene and we just put a methyl group on, see that change? We'll talk about an empirical observation called the Woodward-Feser rules. How do substitutions change the value? We add another double bond in, so now we have a triene. So we have 1, 2, 3, 4, 5, 6 p orbitals. That gets us 3 alkenes. So total from 6 p orbitals, we have 3 bonding and 3 antibonding. That peps this number up, 258. We had the fourth, 290. So we're almost breaking through into the violet region here. We're not quite there yet. So the wavelength is increasing as we add double bonds. Now notice the other relationship. This is an energy value. When it says pi to pi star, so pi means the bonding orbitals, they're filled. Pi star means empty or antibonding. So if we want to take an electron from the orbitals that have it to the ones that don't, it requires that amount of energy for ethene. And as we keep adding the double bonds, notice the energy drops. That means it's easier to take an electron and promote it. And once it's promoted, that means it's higher in energy. So it doesn't really want to be that way. So what happens? It relaxes. And as it relaxes, something has to be given off, and that's the light that you see. So visually, what does this look like? So in the first case, this was our ethene. The second case, that was our butadiene. This was our triene. And then to the very right was the tetraene. So notice 2 p orbitals. We have the bonding orbital. It's occupied by spin-paired electrons. Then the antibonding orbital is empty. The distance between them is the gap. That's the energy that has to be supplied. So notice that distance as we add alkenes. It's getting smaller and smaller. That means it takes less energy to promote the electron. And as we add more and more, then we start getting into these substances that we can perceive in the visible region. See how this pair of electrons is spin paired? We have one up, one down. So when the molecule absorbs that energy, that electron gets promoted and the spin is conserved. So now the molecule has this higher energy. This thing wants to go back to its happy place. And as it does that, that's how the light is emitted. That's the color that we see. Any questions? Yeah.
So if it's a visible color, that means there's no energy needed to fill that gap?
So there's always, if you're seeing color, there's always energy. And that's one thing that you kind of have to just rationalize and accept, that there's always energy around us. When we say like room temperature, 25 degrees C, there's energy. And the amount of energy present is enough to do those promotions that we can see that color. So we're not going to get too much into the theory or math of this, but we want to do some empirical observations like Woodward. So this is R.B. Woodward, and then this is Fieser. So the Woodward-Fieser rules, it's an empirical experiment. So, there are all these research papers published on molecules and then their associated UV data. And what they basically started noticing were these patterns. So there's kind of this thing you need to start with that has a certain starting point as a wavelength. Then there's this library of molecules. How can we make associations with the different substitutions that are happening, and then the output of the lambda max value? So the base compound is the diene, so we need that to be conjugated. That had this value, 217 nanometers. We add the third alkene here, that gets us to 258. We add the fourth, we're up to 290. So there's some trends that we can start seeing just based on the number of alkenes we add. And then if you remember, the lycopene had some methyl groups. How does that affect the number that's observed? So if you're given a molecule that's conjugated, how can you estimate where you would see the lambda max value? The starting point, as I said, is the butadiene. And that's given a value of 217. And basically now we're just going to start saying, what does each kind of substitution do to that value? On average, any subsequent alkene you add is going to be worth plus 30 nanometers. So, just keep imagining you're adding alkenes plus 30 at a time to the base value of 217. So again, that conjugated system, that was the chromophore. In this molecule here, which is called 2-methyl 1,3-butadiene, notice how many carbons it has. 1, 2, 3, 4, 5. That molecule is the monomer by which all of these other things are made. So the methyl group has this term it's called an oxychrome. And it just adds a little piddly amount, plus 5. So, you can think of any functional group and there's probably an associated additivity value for it. So because this was a sigma bond, so sigma bond, that pattern, if we constrain that into a ring where it can no longer freely rotate, that just adds +5. But if we constrain it where the alkenes are on the same side of the sigma bond, that's called homoannular. So you see there that now it's constrained into a ring. That peps it up quite a bit, +39. And then this other example, heteroannular, the starting point is 214. So rather than starting at 217, we start at 214. So that just means that the alkenes exist in different rings rather than just one ring. So let's see if we can remember some of those numbers. Our base value was 217 for that. And we see that this particular molecule now, that's constrained into a ring, and that was the homoannular, so we can say +39. And then we have these other methyl groups bonded. So here and here, there's 2 of them. So the 2 times the 5, that was 10. So that gets us to, what, 6, carrier 1. So I think 266 nanometers. And so that's a way to estimate, given the structure, how can we predict what it should be? So base value. That would be our predicted. Any questions? So again, 266 hasn't broken through the 400 nanometer threshold yet. So if you had a bottle of this stuff, you would not expect it to have a color to it. So let's run through the same thing for lycopene so that we understand this. And I'll highlight in blue. See this alkene here and that one there? They are not conjugated because there's sp3 hybridized carbons separating them. So we're starting from the 217. It says each additional double bond adds +30. What would we estimate on our first approximation for just the double bonds adding? So maybe I should be a little more, have some color fidelity here. I want to make this blue. And then in green, we'll start highlighting the rest. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have plus 30 nanometers times 9. That gets us plus 270 nanometers. And then I'll say 217. We'll just add these together. We get a 7, an 8, and a 4. So 487. So we're just doing the approximation of the alkenes at this point. So we haven't considered the oxychrome contribution yet. So from the base value of the diene, the contribution of the other conjugated alkenes, that gets us up to the 487. So we have, there we are, 487. Let me just highlight the backbone again. So how much more are the oxychromes going to add if they're each worth 5 nanometers? What'd you say?
Plus 30.
A good approximation. So we have 1, 2, 3, 4, 5, 6. But then you need to approximate the other substituent as a methyl group as well. So we'll say the red equals methyl. So 6 times 5 nanometers. That gets us to plus 30, but this other thing coming off, we're going to approximate as well as a methyl group. You know, even though it's not CH3, it's still bonded to it. Methyl-ish, so 2 times. And then overall, that would get us to the another plus 40. So we're at about 500 or 527 at this point. So again, the main thing is, you know, from whatever you're starting with, how all this stuff adds, is it getting you between 400 and 800? So we have 20 minutes left, and I think I can get through this without, you know, a speed run here. So I'll try to take my time, but I do want to do the sniff test here. So again, a lot of this stuff is kind of happening concurrently all over the earth. People at different universities investigating different things. And another area associated with these molecules that was recognized by the Nobel Prizes. So there was a shared one in 1939 by Butenandt and Ruzicka for molecules related to hormones, and then it says polymethylines and higher terpenes. So what exactly is a terpene and how are they related to hormones? So you're familiar with, like puberty, you're a kid, some stuff happens and you start turning into an adult, whether you want to be an adult or not. A hormone is just a chemical that signals something to start, to stop, or to continue. So the broader name for these things are lipids. And you'll see if you go into biochem and other courses in cellular and molecular biology what lipids are structurally. So one of the things is they form cell walls. So there's the lipid bilayer. So you have this kind of polar end, a non-polar chain, then another non-polar chain and polar end that keeps kind of the aqueous environment, the things separated. But imagine a lipid is like you've taken your great value pasta. So it's like a hard stick, you boil it and then it gets like floppy. Imagine you could hold like a handful of them and they're all floppy, right? That's kind of what a cell wall is. You have that one layer and then the second layer, that's the lipid bilayer. And then a lot of biochem talks about how does stuff migrate back and forth through that. So you have these channels like ion pumps, sodium, calcium, potassium, these gates. Sodium comes along, there's some interaction, the gate opens. Any Game of Thrones fans in the crowd? The moon door opens, the sodium falls through. So the lipid bilayers, we won't talk too much structurally about that, but that's the bigger class, and then we dial down into the smaller organic molecules. And these are typically called terpenes. And as I said, they're derived from this monomer, the 2-methylbutadiene, which is known as isoprene. So terpenes, that's kind of just your average CH-containing stuff. When you start putting oxygen in it, then they're called terpenoids. Or the other thing, if the carbon count is not a multiple of 5, then it's a terpenoid because something got added or something got deleted, and it doesn't follow sort of the normal classification. Two examples you're probably familiar with are natural rubber and then gutta percha. So within this square bracket shows how this monomer repeats. So the N means repeating unit. And let me just highlight here. The methyl group is kind of where I look to orient my eyeball. So there's a methyl group. So there's the 3, 4, 5. Then you can see that repeat. The difference between the physical properties of this is the natural rubber has the Z configuration. So Z means same. The gutta percha has E, that means opposite. So just that kind of small structural change makes two different polymers. So just to check the box that I did talk about polymer chemistry this semester. Again, polymers are represented generally through this nomenclature. You have this square bracket here. Then your monomer is contained in that. And then the N is the length of the chain. So, just across the street is the School of Polymer Science and Engineering. So they look at applying organic chemistry to design monomers to do very specific things. So like, spitball in here, but like an airplane. So those airplanes have to be coated with something so they don't ice up, right? So you can make these polymers that are kind of like hydrophobic in a sense. They won't ice up as easy. Any sort of material-based science, you can figure out how to make a polymer to solve a solution in it. So this, I could probably bend this, but it costs a lot of money, and I don't want to do that. But these phones, anyone have one of those bendable phones? Like, I think Samsung makes them. Like you can flop it in half and it becomes smaller. Apparently that's a need. I don't know why people want it, but they did it. That works because of the polymers allow it to do that. If I did this, this would stop working. But the polymers can be flexible like that. And so there's just different applications of it. So as I said, in the box here is the isoprene monomer that can go to these different polymers based on how the reactions are initiated. So the polymerization reaction. I'm going to try to make it through the last 12 minutes here. So I'll take a minute or two to show you this, the first arrow pushing stuff, and then I want to do this so that we can say we've done it. So we might not get through all the slides, but they're kind of self-explanatory from here on out. So there's the monomer. In radical reactions, polymerization reactions are typically initiated three different ways. Either through a cationic intermediate, a radical, or anionic. So I'm just going to draw some general things here to show you the arrow pushing, to show you how it starts. Then another monomer is going to come along and grow out the chain. So I'm just going to say R plus for some reactive intermediate. So that wants some electrons. And the pi bonds have electrons. So the electrons will come out and initiate the chain the polymerization. So because it's cationic, that plus charge has to be conserved, and it'll end up right there because the electrons from the pi bond formed a new sigma bond here. Then we talked about resonance with the Diels-Alder reaction. So if we draw a resonance form of this, we can then move that plus charge to the end, and then another monomer will come along and do the same thing. So you might ask, how does it stop? Like, why don't we live in just like one long polymer chain on Earth? There's other things that will terminate it. So if you have some anion in there that will trap it, that'll cap the end. And again, that's a lot of what the polymer science people do is we want to put very specific functional groups along the chain or at the ends. That's going to affect the physical properties so that we can make these neat materials that we use for different applications. Maybe let me just say the radical and the anionic, you're going to do, the radical is going to move a single electron. The anionic, since it's negative, it's going to attack the dying. So the arrow will flow the other way. Let me see where, so maybe I'll let you push those arrows for that here. Let me advance this slide. Take a break. I want to prepare this stuff. Basically what I'm going to do is just dip some Q-tips in some things, pass it around, you can smell it, and I'll hand out a sheet and sign in. So the blue cup is going to be so the blue cup is going to be our carbone. And once I have all this stuff set, I'll show you the structure to you, but all I'm going to do is dip this in here. It's a liquid. I'm going to put the Q-tip in the cup, pass the cup around. Don't just smell it, that you don't got to like lick it or put it up your nostril or anything. So start here, just give it a smell, pass it around. So the purple cup here is the S carbone. So we have R and S. These are enantiomers of one another. See if you can smell the difference between them. This is the S. I went to the corner market last night. Don't think I'm bougie. Needed some milk. Stopped by the spice aisle and bought pure peppermint extract and pure mint extract. We'll see if they evoke any emotions. So we want mint and yellow. Here's the mint. Peppermint. What is the difference? Peppermint. Let me hand these out and then I'll talk through these last couple slides. So just fill in your name, your ID, and the letter A.
Oh, that's all different though. But like if you take out the sugar. They don't use it unless it's sweet. To polish it? They use it for the mint one. I use the mint. I was talking about the mint. Strawberry. Don't do gum. And I got some like that caramel. I like the caramel piece, but then they just default to it.
So while you're doing some sniffing and filling out your sheet here, the terpenes, as I said, they're all made from the 5-carbon unit isoprene. So everything has to be a multiple of 5 except the 5 itself. So this is where the nomenclature gets a bit strange. A monoterpene has 2 isoprene units. So 2 times 5, that's 10 carbons. Sesqui, apparently that means 1.5. That has 3 isoprene monomers, that's 15 carbons. Diterpenes has 4 total monomers for 20 carbons. Sester, 2.5, that gets you to 25. And then tri is 6, so that gets you to the 30. So the things you're smelling are basically essential plant oils. So if you're into like aromatherapy and that sort of mojo, if that's your thing, there's these stores where you can buy these oils. You can make your own perfumes and fragrances. I have like a 16-year-old bottle of Polo Black that I occasionally shoot on my neck if I'm feeling frosty. It's not as strong as it used to be. You can tell it doesn't have the punch anymore. But if you have cologne or perfume, the underarm stuff, there is some small molecule in there that's giving it that fragrance. And so that's a pretty big chemical industry, is just taking these essential oils, mixing them, and then having a fragrance. So maybe the peppermint is menthol. I don't know. Did you get any menthol notes from it? You start using those terms. Did you notice a difference between the 2 Carvone ones?
Yes.
So apparently, I think it's the S Carvone is supposed to smell like rye bread. And then the R is more spearmint. So there's the structure of Carvone. So that's a C10. So that would be I guess it's a terpenoid because of the oxygen, but a monoterpene. So 10 carbons, that's a monoterpene. And they're mirror images of one another. So one's R, one's S. That's due to the stereogenic carbon. So the same molecular formula, weight, just the difference between the spatial configuration. And maybe you perceived them as, how many really did it smell very different to you, or you couldn't tell? So if you think about the reason why that is, like why do they smell different? So they're volatile, that's how you can smell them, but they're hitting your olfactory senses. So that molecule is hitting some enzyme which is triggering this process for you to perceive it. So between the 2 structures, they're fitting into those enzymes differently, and that triggers your perception that they smell different. So I think the rest of this stuff was just some questions and whatnot that you can go through to identify, is it a monoterpene, di, that sort of thing. You can either count the carbons or see if you can identify the isoprene units. That's how you solve that. So we're at time right now. If you want to bring your sheets up for the attendance, your exam opens now for 24 hours. It closes tomorrow. Please don't forget to submit it. Just circle in A for the response.
last one.